So this is the team working on this project. Basically me, Shizan, Orly, and Trevor, our chief scientist, which is also professor at Berkeley. And I think we are all here at the conference, so feel free to reach us if you want to know more. So I will start to speak a little bit about Nexar, the open data set that we shared in the beginning of the year, a little bit about the challenge, the leaderboard, the winner solutions, and then we'll share some insights. So Nexar started 10 years ago with the mission of making roads safer. And we start doing that by producing dash cams that you can install on your vehicles. And early on, we started detecting every kind of incident like hard brakes, harsh cornerings, and so forth. And every time we detected that kind of event, we recorded a video on our cloud. So today, we have over 350,000 cameras in the US installed on our customer base. And we have recorded more than 60 million videos of these kind of incidents. And we are working in several fronts, like 3D reconstruction and so forth. But the most related with the work presented here, it's related to how do we search this large database of videos to look for edge cases, collisions with pedestrians. So everything that might be of interest, especially for the AV community. And so the focus of this competition was on traffic accidents, which cause significant loss of life and financial damage. We believe that with our massive collection of videos, we can help the AV industry moving forward with the anticipation of these kind of cases and reduce the fatalities. So the question we start by doing ourselves is, can we help anticipating collisions with the front camera only, because that's what our dash cams have. It's a front-facing camera, road-facing camera. And we looked into a sample of 2,000 collisions, and we found that most of them happen on the front of the agro vehicle, and most of them were also between cars and trucks, between cars or cars and trucks. So this motivated us first to release an open data set. We try to provide high-quality videos and also show a bit of what our database looks like, and to help advance the research on this important problem of collision anticipation. So about our data set, it's 1,500 high-definition videos, each with about 40 seconds. And we covered most important US cities, and we tried to cover also different weather conditions, lighting, and different scenes like urban, suburban, highways, and so forth. One question we had was how to annotate for temporal events. And we looked to some of the data sets that are out there released in the community. And we found that most of them either had the time of appearance, which is the time when you see the third party for the first time, which, for instance, in this example video, it's at time 0. And we didn't find it to be super helpful for what we wanted to do. Or we also see the time when the collision is imminent and there's actually nothing you can do. So we proposed, in addition, of course, to the time of collision, to also add the time of alert, which is, it's rather subjective, but it's something that when should you take action? When is the moment that you understand that some action should be taken, like hitting the brakes or the wheel? And because it is subjective, we asked 10 annotators to annotate for each video this time of alert. And then we adopted a conservative approach where we went for the second shortest interval. And you understand why, because we use this time of alert to understand how far in time is an accident predictable. So this is the distribution of the alert interval. You get the alert interval by subtracting the collision time and the alert time. And so this is the time of reaction. It's the time you get to react to a potential accident. And we see that in our data set, we have some samples where this time of reaction is under 1 second, which can be too much for a user. So if you send a beep to a user for a user to react, but because we are targeting not only aftermarket devices, but also autonomous vehicles, which can have shorter reaction times, we left these accidents which are more difficult to predict in the data set. So this is looking to the challenge. This is an example of a video on the test set. So basically it's a 10-second video, and the video stops at a given time, and the model should say how likely it is for an accident to occur shortly after. And as the goal, we want to predict accidents as early as possible, while minimizing false positives and maximizing recall. So looking to the literature, we saw that these were also the typical goals of the papers out there, but we found that these were split by two metrics. One typically dedicated to the time to accident, so how much time in advance can a model predict, and another which was related to the precision and recall, typically the area under the curve or the average precision. And here we propose to use a mean average precision, which tries to unify these three goals into a single metric, which was also important for ranking our leaderboard using a single score, single metric. So how do we do this? Basically, we define three thresholds, 500 milliseconds, 1000 seconds, and 1500 milliseconds, which are how much time in advance, how much time you before the accident you cut the video. And so, of course, if it's 500 milliseconds, the accident will happen shortly after, in the case of a positive example. If it's 1.5 seconds, it's probably more difficult to predict because you have 1.5 seconds until something happens. And so we take this, the average precision of at least three thresholds, and we find the average, the mean of the three. One important aspect to point out is that we use the alert interval to understand if a given video can be cut, for instance, at 1.5 seconds. If we have, for instance, a reaction time of 1 second, that video cannot be made part of the average precision curve of 1.5 seconds, because at 1.5 seconds, that incident is not yet predictable according to our annotators. So regarding the participation in the challenge, we had almost 300 participants and over 1,600 submissions on a challenge that was up for 12 weeks. Well, and we were quite happy with the adherence. And as a leaderboard, on the first place, we have Paul Anderson. Paul Anderson is actually the CEO of a company, 3 Lines of Code, which has a booth here in CVPR, and I just talked to him. He's currently not here, but he will be also demoing his solution for this challenge in his booth. On the second place, we have 2 students from China universities, and on the third place, we have an independent data scientist. So quite diverse top ranking. We also have honorable mention to a team from the Yuan University, which got a very high score also, but there were issues in their submission, so that we had to leave them out. But their approach was quite interesting. So looking to the approaches of the different teams, on the top two places, we see a trend where using video transformer models had the best results. On the third place, we saw a simpler approach based on looking into the optical flow and using convolution networks. And another popular solution that we see was looking to the frame as individuals and getting some kind of encoding or embedding for each frame, and then trying to use a GRU or other recurrent neural network to capture the temporal aspect. And by the way, this was also the solution proposed by ChatGPT when I asked him how do we solve this challenge. So, and it was quite popular. So I'll speak a little bit about the main, the top three places. So in the top three in the first place, we have a video transformer, not a large one with 35 million parameters. And here, the main advancement was done by using the 3 lines of code tool to inspect the instances, understanding things like confusion, where are the areas where are confusions between positive and negative examples, some of those examples, weighting the instances, and so forth. So with this kind of iterative refinement of the training data, Paul was able to get from 0.7 to 0.9 without any fine-tuning or any manipulation of the network. On the second place, the team used a much larger video transformer with 1 billion parameters. And they did the full model fine-tuning with the training data we provided. And one interesting thing to point out is that there are a lot of decisions here to be made. Decisions related with the sampling. So where do you start sampling the positive examples, how far? Also balancing strategies, because you can use the positive videos for both getting negative and positive samples. And the team didn't explore that too much. And so we believe there is potential for this model, also on optimizing these decisions, but also if we feed more data, we should also see higher returns. And finally, on the third place, basically the team used simple URL to get the vehicle masks to do the segmentation, and then optical flow by calculating the differences between two frames. And this was enough, together with 2 ResNets that were ensembled, to provide a score that was not very far away from the rest. And this was like inspired from the Dutch theoretical driver license examination, where students are presented with a single image and they need to decide what to do, if they will hit the brakes or if they will continue driving or any other action. Also, the solution is a complex. Here it's very simplified because the author uses several instances and does an ensemble. It doesn't only uses 2 frames. So we analyzed the top 10 teams, and basically we optimize, we transform the submissions of every team so that we can have binary decisions for each team, and we calculate the difficulty score as, for this video, how many teams failed classifying the video. And so this will give you a difficulty score between 0 to 1. And one study that we did was comparing how much more difficult it is to predict 1.5 seconds in advance versus 0.5 seconds. And we see kind of a linear This is very limited to the three points in time that we are measuring. So, but still, it's interesting to quantify that adding 3 times more time in advance makes the problem 3 times harder, according to our metric, to predict. Another insight was that the teams have much more difficulty in setting highways. So we have 25% failing on urban scenarios versus 16% on highways. And fog was super challenging. We didn't have a lot of examples with fog, but every time we had fog, the teams failed. So here are some difficult cases across all teams. These are just examples. So you see a vehicle that is crossing a red light. And this is the kind of video that teams had difficulty. So most of the teams failed that video. This is another one. If you see a car that is leaving the parking, and this will result in a near collision. And most of the teams also didn't see that. Here's another one, and on the right you will see a vehicle leaving the parking, and it's subtle because it's very difficult to predict, but still it's interesting to look to some of these examples and try to understand. And this is a very recurrent pattern, which is the car on the front brakes, you start braking, and we don't know if this will result in a near miss or a collision, or if it's a normal, regular driving situation. So where next? So we'll be at ICCV in the Too Cool workshop, where we'll be presenting the method that we are developing in-house. We are also hosting a workshop in Porto, Portugal, in the end of December, probably. So stay tuned. We will have the first place that are presenting their solution in more detail. And we also have invited speakers and some of in-house speakers. Just yesterday, we released the test set that we used on the competition, including annotations and a script that allows you to evaluate your own solution in a very simple manner. And we're also looking into the ML dataset and annotating the alert time so that we can extend the dataset and apply our metric there. So key takeaways. So we've introduced the alert time, which we found to provide interesting and useful insights. We introduced the mean average precision as an unified metric for tackling recall precision and time to accident. We released an open data set, including a test set with ready-to-run evaluation, and we provided insights on key solutions from the community in this challenge. So here are some useful links, the blog post that we wrote about this, the data set that's on Hugging Face, the competition that's on Kaggle, and reports from the winners from the first 3 places. And that's all, folks. Open to questions.